Today we start about projection operator. Okay, projection operator. We also start from definition of projection operator. So write this definition now. Let X be a linear space. Let X be a linear space and let P x to x. Let P x to x be a linear operator such that p square equal to p. Okay, then p is said to be projection operator. Then p is said to be projection operator. Okay, now we write here p y, here x to y subset of x, then p x equal to x0 or px equal to x where x belongs to y and px equal to px where x does not belongs to y. Okay, here px to y subset of x defined in this way. Then what we do px be a projection operator. We see this, just write p square x equal to p of px. Okay, then p of y, px equal to y, then p of y equal to y if px equal to y. Okay, and since y belongs to this y, so this one hold, this implies that pba, this implies p square equal to p, so pb projection operator. Here y equal to px again, right? Then p square equal to p, and so p be a projection operator. So p be a projection operator. Now we write definition of another one. It is this portion. Now we write definition of this. Let X be an inner product space. Let X be an inner product space and let px to x be a projection operator then P is said to be orthogonal if RP perpendicular NP, that is RP equal to NP perpendicular. So X equal to RP NP direct sum. Okay. Now observation. Now we write observation if Px to x is an orthogonal projection operator, then first RP and NP are closed spaces and number 2 x equal to RP NP direct sum. Okay. Then next how we discuss, we write the statement of this theorem. Let X be a Hilbert space. Let X be a Hilbert space and Px to x be an orthogonal projection operator and Px to x be an orthogonal projection operator then P be linear and bounded with norm P equal to 1 if P not equal to 0. Okay. So we write to prove of this. Let P not equal to 0 and x belongs to x, then x equal to RP direct product of NP. Okay. Then y equal to Px belongs to RP equal to y. Then x equal to y plus z. Then x equal to y plus z for some z belongs to NP. Okay, now is our portion. Now norm of x square equal to norm of y plus z square equal to norm of y square norm of z square. This implies norm of x square equal to px square plus norm of z square. This implies px square less than equal to norm of x square. This implies norm of px less than equal to norm of x. Thus p is bounded with norm p less than equal to 1. Okay, again note that norm p equal to p norm of p square less than equal to norm p whole square. This implies that 1 less than equal to norm p. So from 1 and 2, since p not equal to 0, okay, hence from 1 and 2 we get norm of p equal to 1. We erase this portion and going to further discussion about that. Now we write here, let X be an inner product space. Let X be an inner product space and define Fyx to Ky and define f x to Ky Fyx to Ky Fyx equal to xy for all x belongs to x. Then first Fy be linear, second Fy is bounded with Fy is bounded with norm of Fy less than equal to norm of y. Okay, now we're going to discuss about that. Fyx equal to mod of this equal to mod of xy inner product of less than equal to norm of x norm of y for all x belongs to x. So Fy be bounded with norm of Fy less than equal to norm of x. Sorry, norm of y, here x. Okay, again we write here Fyx equal to xy less than equal to norm of Fy norm of x, xy not equal to 0. Again, so y square equal to norm of y less than equal to norm of Fy norm of y. This implies that norm of y less than equal to norm of Fy. This marked as 2. Okay, hence from 1 and 2. Hence from 1 and 2. Okay, hence from 1 and 2 we get norm of y equal to norm of Fy. Okay, next we write one definition. We erase this portion and going to one definition of that. Now we write definition of something. Let C be a non-empty subset, closed subset of a Hilbert space. Let C be a non-empty closed subspace, non-empty closed subspace of a Hilbert space X, of a Hilbert space X. Then there exists PCX to C such that norm of X difference PCX equal to infimum of norm of X difference Y belongs to C for all X belongs to X. Then PC is called metric projection operator. or nearest point projection operator. Okay, now let C be a non-empty closed subspace of a Hilbert space X. Then there exists PCX to C such that norm of X difference PCX equal to infimum of Y belongs to C norm of X difference Y. Then PC is called metric projection operator or nearest point projection operator. Okay, now we discuss one theorem. We write the statement of this theorem first, then going to proof of this. Let X be a closed subspace. Let X be a closed subspace of a Hilbert space X. Of a Hilbert space X. Then first X equal to Y plus Z and P. There exists a unique orthogonal projection operator. There exists a unique orthogonal projection operator Px to x with Rp equal to y and norm of P equal to 0, 1 if P equal to 0 and if P not equal to 0. Number C. Norm of X difference Px equal to infimum of Y belongs to Y. Norm of X difference Y equal to D. Okay. So let X be a closed subspace of a Hilbert space X. Then A Y X equal to Y direct sum of Z. B. There exists a unique orthogonal projection operator Px to X with Rp equal to Y and norm P equal to 0 if P equal to 0 and 1 if P not equal to 0. And C. Norm of X difference Px equal to infimum of X difference Y D equal to D. Now we also going to this proof of that. So X be a closed subspace of X. Then first X equal to Y direct sum of this. If Rp equal to Y, then that means X equal to Y inner product of Z implies there exists a unique orthogonal orthogonal projection operator P projection operator E x to x such that Rp equal to y, such that Rp equal to y. Okay. Again, C, how we just prove C. This one is we write here. How we prove this one? Then this two, then A x equal to y in direct sum of z, and there exists a unique orthogonal projection operator P such that Rp equal to y, and this one is projection operator. Now C equal to we prove C. Okay, now we prove C. So we erase this portion and write just C here. Let x belongs to x. Then Px belongs to Rp equal to y. Now x difference Px belongs to R of I difference P equal to Np equal to Z. So this one equal to Rp plus Np. Okay, A, B, we will mark it this one, then C. So how we write? We write here Px belongs to y. Okay, then x difference Px belongs to z. Or Px difference again, and Px difference y belongs to y. For all y belongs to y. So now note that x difference y square, norm of this square equal to x difference px difference y square equal to norm of x difference ps square and px difference y square. Since x difference px belongs to z and px difference y belongs to y, so this one, since y intersection z equal to 0. Okay, hence x difference px norm less than equal to x norm y. That means this square less than equal to this implies x difference px less than equal to norm of x difference y. Okay, for all y belongs to y. This we marked as 1. Again note that y be a closed subspace. We erase our portion and going to further discussion about that. Note that y be a closed subspace of x, y be a closed subspace of X, then there exists X0 belongs to Y such that norm of X difference X0 equal to infimum of Y belongs to Y, norm of X difference Y equal to D. Hence from 1 X0 equal to Px marked as 2. So from 2 we get X difference X0 equal to X difference Px equal to infimum of Y belongs to Y, norm of X difference Y. Okay. So we just do that. Here we also prove this, and now we'll stop. Okay, but first one we now again discuss here. First one, that means X equal to Px, X difference this one, then this belongs to Px belongs to Y equal to R of P, and X difference Px belongs to N of P equal to Z. Okay, so X equal to Y this set. So today we stop here.